Okay, welcome back, everybody. This is the first lesson of our new unit, and we're going to talk about a method of thinking called inductive reasoning. So let me tell you what that is first, and we'll look at some examples of inductive reasoning. And after the notes today, then we'll have you do that assignment. It's already up on Google Classroom, and you can take a look at that. Okay, so what is inductive reasoning? So inductive reasoning is when you notice a pattern and assume that pattern will continue. So for example, if I write a pattern up here, I'll write some words. This is Monday, Wednesday, Friday, and then the job will be to write the next word in the pattern. And so if you notice a pattern, they're starting with Monday and skipping a day. So they're writing every other day. So if we notice that pattern and assume that that pattern continues, we go Monday, skip Tuesday, Wednesday, skip Thursday, Friday, skip Saturday, and the next name I should say would be Sunday. So you're going to arrive at Sunday based on inductive reasoning. Let's show another example of when we use inductive reasoning. So let's say they have the number sequence 3, 6, 9, 12, 15, and then you're supposed to write the next number in the sequence. Well, if you notice that every time we're adding 3 to the previous number to get the next one, so if we continue that pattern, we're going to say that the next number in that sequence is 18, based on inductive reasoning. Let me show you another example of inductive reasoning, this time with symbols. So let's say we have an arrow pointing to the left, and then an arrow pointing at an angle a little bit from the first one. Then we have an arrow pointing straight up. And then you're asked to find, well, what do you think is going to come next in that sequence of arrows? And so it looks like we're rotating the arrow 45 degrees clockwise every time. And so you're, based on inductive reasoning, would probably say that the next picture would look like this. Another arrow 45 more degrees clockwise. So when you do that, you're using inductive reasoning. Okay? So a statement that you make, a statement based on inductive reasoning is called a conjecture. So there's some vocabulary for you. A conjecture. It's really what you think is going to happen next. So let's look at our next example. Complete the conjecture. Here's the conjecture. The product of an even number product of an even number and an odd number is blank. The product of an even number and an odd number is blank. So you might start giving yourself something to work with, some examples, and say, well, I got to pick an even and an odd number and multiply them together and see what I get. So if you take 2 times 3, that's an even and odd, you'll get an even. Well, that doesn't prove anything. Let's say you choose two different numbers and say 2 times 5. All right, well, there's an even and an odd there. And you get 10. Well, that's also even. Well, try some more. So here's an even and odd, 4 times 3. Multiply them, well, you get 12. Well, we've got another even number there. Take 4 times 5, another even and an odd. That's 20. So every single example you can come up with, when you chose an even number and an odd number, you ended up when you multiplied to get an even number. So your conjecture is that that is going to be an even number. Doesn't mean that it is, because there could be some combination of odd and even numbers that you have not thought of that would not be even, that would be odd instead. But based on what you have kind of thought about, you think your conjecture is that that product is going to be even. Okay. Here's another one for you. Example number 2. Same thing here. And that is complete the conjecture. The product of 2 odd numbers the product of 2 odd numbers is blank. So again, maybe you'll come up with some examples. Well, let's take 3 and 5. So those are both odd, 3 and 5. They get 15. Take another couple pair of odds, 5 and 7. 35. Well, both those are odd. 7 and 9. 63. That's odd again. 7 and 11. 77. So based upon your inductive reasoning, you'll say that you think that the product of 2 odd numbers is odd. Again, that's your conjecture. Okay, so let's talk about that a little bit more. Talk about how the fact that a conjecture could be true or false. Okay, so to show that a conjecture is always true, you must prove it. In case you're starting to think where this is all heading, yes, we prove theorems in this class, so we have to know how to prove things. So to show that a conjecture is always true, you must prove it. 4 examples is not a proof. However, to show that a conjecture is false, you must find a counterexample. You only need one. If you can find one situation, one case where the conjecture is not true, you can stop. You've proved it false. You don't need to use more than one. Just one will do it. Okay? So let me kind of summarize the whole process of inductive reasoning, and then we'll do one more example. So here's kind of what the whole process looks like for inductive reasoning. We also have deductive reasoning, which is actually more common than inductive. It's just a different way to think. First of all, so if you want to use inductive reasoning, you're going to look for a pattern. Look for a pattern in the data, whether it's a picture or numbers or words or whatever. 2, make a conjecture. That's basically what you think is happening. Make a conjecture. It's your best guess as to what's happening. And then after you make your conjecture, prove the conjecture. So either prove the conjecture or find a counterexample, which would mean it's false. Okay, so that's kind of the process. Let's apply that process to one more example here, and then you should be able to do the assignment, which is posted. Okay, so here's our last problem. I think this is example 3. And that is to show that the conjecture is false by finding a counterexample. Okay, so this time the conjecture comes in the form of some algebra. So here's the conjecture. For all positive numbers, n. So any positive number you can put in for the variable n. The conjecture is that 1 divided by n is less than or equal to n. Okay, so you can probably find some numbers for n that would make it true. So for example, if you let's say n is 7, so that would give you 1 over 7 is less than or equal to 7, which is true. You have not proved your conjecture by showing that one example. Let's choose another one. N is 12. So put 12 in for n. So 1 over 12 less than or equal to 12. Yep, true again. And again, 2 examples don't mean that conjecture is true. And to find one number for n that makes that statement false, that's our counterexample. And so our conjecture in that case would be false. So what if this time I choose n is 1/2? That's a positive number. Doesn't say it had to be a whole number. So if I put 1/2 in for n in both spots, I got 1 divided by 1/2 less than or equal to 1/2. 1 divided by 1/2 is 2. There's 2 1/2s in 1, so you'd have 2 is less than or equal to 1/2, which is false. I can stop a problem there because I have found that 1/2 makes that conjecture false. I don't need to find any more. I just need to find one. because that conjecture must be true in all cases. And we found one case where it is not true, and so the conjecture is false. Okay, so we're learning about different types of thinking in this unit, and it's kind of an introduction to proof. And that's a big part of geometry, so that's where it's headed. Okay, there you go. Good luck in the assignment. Thanks. Bye.